So I want to go over really quickly solubility rules and precipitation. So earlier we showed a little video clip, and you may have to go back and look at it to remind yourself. I actually have the second half of that video I'll show you. But we took sodium carbonate and calcium chloride, and we made solutions out of them, right? Now think about what it means now in terms of electrolytes. When I took the sodium carbonate and the calcium chloride and I put them in their separate beakers, these dissolved, and because they dissolved, you know that they broke up and formed electrolyte solutions by splitting up into their ions like this. And we know this just because they made these homogeneous mixtures. They dissolved. And the only way that ionic solids dissolve is by forming these ionic solutions or these electrolyte solutions. I do the same thing with the calcium chloride like this. Right? I put the calcium chloride and I added some water to it, and then I'm going to end up with calcium ions, and then I'll have chloride ions like this. So now the question is, what's going to happen? Because I'm going to take these two solutions and mix them together, and then we have to see what happens, and then we're going to talk about how do we know that's going to happen, and what do we call this sort of process that's going on. So this is the end of the video that you saw before. On the left is the sodium carbonate solution that we made. On the right is the calcium chloride. And you know, they're soluble, so the ions are floating freely in solution. But what I want you to see is what happens when these two solutions are mixed, and so we're going to continue with the video from here. So when I pour the solution in, I guess what you should be noticing is that it becomes immediately cloudy. And that opacity or opaqueness, right, is the result of a solid forming when the two aqueous mixtures are mixed. And so this is an example of a precipitation reaction when you take two aqueous solutions and you mix them together and a solid forms from the two aqueous solutions. So calcium chloride and sodium carbonate form a precipitate when mixed. Okay, so this is what I want to do. Let's write out in a chemical equation what we think might have happened. So I have sodium carbonate, so I'll go ahead and write that. That was the solution on the left. And it formed an aqueous solution, so I'll write AQ, and we mixed it with calcium chloride, CaCl2, and that was also aqueous. And then they formed product. Now let's think back. When these solids were dissolved in water, they formed these aqueous solutions, so we know they split up into their ions. So it would have been something like a bunch of sodium ions and then carbonate ions. So I could do two sodium ions if I really want to balance it. But since the reaction isn't actually balanced yet, it really doesn't help us that much. We'll go ahead and do it just to be on the safe side like this. So those are my ions from that. And then in my calcium chloride, what I did is I got calcium ions and I got some chloride ions like this. Right? So that's what happened. This is actually what the solution looks like when it was mixed. There's just a bunch of ions floating around. Now the question is, what are the possible products that can form from this? So the way you do it is you look at the charges of the ions and you think opposites attract. This is Coulomb's law. I've made mention of it before, I believe. But the idea that oppositely charged objects are attracted to each other. It turns out two negative ions can't get together and form a compound in chemistry, and two positive ions can't. But a positive and a negative can. So think about sodium. Sodium came to this party, let's think of it as a party, with carbonate. But it's a positive charge, so it wants to leave with chloride. So a possible other product is sodium chloride, table salt. Now, what's the other possible product? Well, if this positive ion is going with this negative ion, then this negative ion has to go with this positive ion. So when we write the formula, we always put the metal ion first or the cation first. So that would be CaCO3. So those are your products. Now here's the thing. It was cloudy, so we know that a solid formed in the solution. Right? It was cloudy, so we know a solid formed in the solution. Now, from your experience of dissolving like salt in water, right? What do you know about salt in water? Is actually that it's aqueous, that it'll dissolve. So this is actually aqueous. So in reality, there's a reaction arrow here, and I have a sodium ion, and I have a chloride ion like that. So that means the only other compound that could have formed is calcium carbonate, and this is a solid. So if I'm thinking about what's happening on this next line, is that it's calcium carbonate as the solid like this. Now, this reaction, that top reaction, we need to balance it, and we've gone through that before, but I'll go ahead and balance it. It only requires the one coefficient there. So really, in this bottom part, I have 2 sodium ions, and I have 2 chloride ions like that. All right, so the only things that actually did anything in this reaction, because you notice the sodiums on the left are floating around, and the chlorides on the left are floating around, and on the right, they're still floating around. So they didn't do anything. The only thing that did anything is the calcium carbonate that was formed, and then the calcium and the carbonate ion on this side that got together. The rest of them just sort of were spectators, and we'll talk about this in more detail. The rest of them were just spectators to the calcium and the carbonate doing a reaction. Okay, so I'll skip the next slide because I got a little carried away. And this is the next slide. So what happens when they're mixed, right? I kind of got it past myself. I said what happens when they dissolve, and then I went into what happens when they mix. Well, when they mix, a precipitate forms. So calcium carbonate is most likely not soluble in water because the sodium chloride we know is. Now, let's say you wanted to know if something was soluble. You don't want to have to do this process every single time. So what chemists have come up with is a list of compounds or ions that are generally found in soluble compounds, and a list of ions that are generally not found in soluble compounds. So these are known as the solubility rules. So here's a bunch of solubility rules, and most of them are actually based on anions, except for that first rule. It says, for example, it says compounds containing the following ions are generally soluble. So if you have lithium, sodium, potassium, or ammonium ion in your chemical formula, most likely you're going to be a soluble compound. The same can be said to be true of chloride, bromide, and iodide, the halides, the halogens, and sulfate, and then nitrate and acetate over here. Right? These are nitrate and acetate. Now notice what it says here, though, for chloride, bromide, and iodide. Even though they're generally soluble, there are some ions that will cause them to precipitate out of solution, or some ions they will cause to precipitate out of solution. And those happen to be silver, mercury 1 ion. Now there's a 2 plus here, but each one's plus 1 because there's 2 of them here, so it's mercury 1 ion, and lead 2 ion. Those are generally insoluble. And then sulfate, if it pairs with the group 2, the alkaline earth metals, many of those are not soluble or slightly soluble. So if it gets together with strontium, barium, or calcium, those are generally insoluble. And again, lead and silver are not soluble as well. So those guys precipitate out with all kinds of other ions. So those are the solubility rules for the things that are generally soluble, and we also have a set of rules for the things that are generally insoluble, is the word we use for things that aren't soluble. And again, the exceptions are things that are insoluble. Now let's look at the other rules, solubility rules. The compounds containing the following ions are generally insoluble. That means they'll precipitate out. So hydroxides and sulfides tend to make insoluble compounds, except, you notice the first exception? That's the things that are always soluble. So that's actually a good list to remember. The group 1s in ammonium and acetate are generally soluble, and nitrates are generally soluble. That's a good list to remember. But it says when sulfide, right, compares with calcium, strontium, or barium, the compounds are soluble. Or when hydroxide combines again with, these are the alkaline earth group 2A metals, many of those are also soluble. Now, carbonate and phosphate, with their high negative charges, usually strongly attract positively charged ions. So those are almost always insoluble except for with the group 1s, ammonium or ammonium ion. So let's do a little bit of practice, right? We're going to have to go back to the solubility rules. I'll do the first one for you to see where we go with this, and then you'll have to do the other two by going back and looking again at the solubility rules. So, sodium oxide, Na2O, what we need to do is look back at the rules and decide whether or not sodium is soluble or oxide is soluble. Now, normally you look at the anion, but when you flip back to both of these, right, there's no oxide listed here. So what we have to look at is the sodium, and the sodium can be found here as generally soluble, and there are no exceptions. Right? You would have seen it also here, right? But that's not for oxide. Sorry, that's not for oxide. So, but generally soluble rule here, right? Lithium, sodium, potassium, ammonium are generally soluble, and there are no exceptions. So what I want you to do is say, then we would write that this is aqueous. And because it's aqueous, we can tell that it's going to break up into 2 sodium ions and an oxide ion like this. Now, you should technically write AQ at the end of each one of these, but I generally cheat and I draw this squiggly line, because that's like wavy water, to represent aqueous. So if you want to do that, you're welcome to do that. Okay, so I want you to determine whether or not it's soluble, and then if it is soluble, I want you to write the numbers of each ion that come out of that compound. So go ahead and look at the next two, and then when it comes back, the answers will be on the screen. So go ahead and pause. So when you look up barium sulfate, you'll notice that barium's not in this list, but sulfate is here. It's generally soluble, but when it pairs with, and there's barium, right, it's insoluble. So its state would be solid. That's where this came from. And then I wrote sulfate, generally soluble except barium. I didn't write all the other exceptions. I just the one particular for this problem. So go ahead and do the same thing with aluminum sulfate. Okay, so sulfates, oh, I forgot to put aqueous. Sulfates are generally soluble. Aluminum is not one of the exceptions, right? So you can look down here. You don't see aluminum. Silver is there, but I did that on purpose so it would maybe trick you. But anyways, how many ions did it produce? Well, 2 aluminum ions and 3 sulfate ions. There's a lot of ions in that guy. There's actually 5 ions in the aluminum sulfate when it breaks up.